let's see what we have learned so far. So far, we have gone over the most important part of classical time series analysis. We have learned to describe time series data, decompose, find ACFs, PACFs, identify ARIMA models. We have tried different approaches to model time series, such as time series regression, with autocorrelated errors, ARIMA models, exponential smoothing, vector autoregression. And we have also learned to do something that is very popular now these days, which is forecast ensemble. In your last homework, right, you combine the forecast instead of choosing the best forecast. Remember that in your homework too, you had to create a table at the end of the homework in which you showed the forecast from each of the method and the root mean square error of each of the methods. And then you had to also calculate the average forecast and compare the root mean square error of the average forecast with the root mean square error of the forecast that you obtain individually from each of the models. That is very, very popular these days. Typical, as you can see in these pictures, we get different approaches to model a time series. And within these approaches, we forecast with each of them, and then we obtain the average. Okay, because none of the members of the ensemble, this is called now a very popular term, ensemble forecast, none of the individual forecasts does great, but when you average them, that's the one that does the best. And that is used a lot by financial institutions or even the government. Everybody that is forecasting the future usually will look at forecasts from different forecasting companies, and they will average, or even there is an institution that I will post separately so that you can see how they do it, that compiles the forecast of about 30 or 50, about 50 companies, and then calculates the average of those forecasts. And that's what is called the consensus forecast also. And that is something that everybody looks at for making their forecast. So that's ensemble forecasting. So that's what you did in your last homework. Find forecasts with several time series analysis methods, and then you combine in an average of all forecasts. In order to do that, you had needed to learn several methods of doing time series fitting and time series forecasting. And that's what we did in the last weeks of this quarter, classical time series analysis. There was a limitation, though, in what we did, is that we had complete observations all the time. We have regular sampling intervals. We had data sets that were collected in every single sampling interval. So we had no missing data. And I purposely forced that into the learning so that you could learn the methods without any of the difficulties that come when you have to spend a lot of time doing data cleaning, data management, thinking, oh, what am I going to do now? I don't have these conditions. But now we're getting into this situation. Okay, so sometimes we are going to have many time series, and that's very typical. The case of Walmart, of Facebook, of Kmart, of any company that or any institution that is in the study of time series. Astronomers have numerous time series. So the idea is that none of those time series are complete. Sometimes they are not collected at the same sampling interval because there is no interruptions, the machines break and they don't collect the data during that time. Or maybe by the nature of the data, like a stock market, the stock prices are not collected during the weekend. So you don't have the conditions that we have had until now that I imposed and are actually prevalent in many time series, particularly government time series and business time series tend to be very complete and very uniform. But as we use the internet, as we use sensors to collect data, and we rely more on machines for data, machines break, and we have worse conditions for our time series. So what happens in those situations? Well, we may not be able to use the classical approaches to time series learn so far. And we might not get to the point that we got in the last homework, which relied on time series with complete observations, sample at the same sampling interval, and without interruptions. So as a solution, we could aggregate to solve the problem. For example, we could make daily data monthly, aggregated to avoid the missing values, the missing some days not being collected, or make the hourly data daily because we might miss data for some hours. And then we could use the classical approaches, learn so far, make the data TS, and then use all the facilities that come with the TS machinery in R. Or alternatively, we could indirectly make use of what we already learned in classical analysis to do other type of analysis that people that don't know time series are doing these days with time series. So maybe we just want to classify the time series. For example, we might want to be able to classify our customers based on their pattern over time. We might want to classify stars by their luminosity over time. We might want to classify rivers by their river runoff over time and so on. So we might be interested in clustering or classification, or we might want to know the temporal electricity use of different businesses. So that requires new approaches that both take into account how the data is collected, which causes problems of missing data, non-regular intervals, and so on. So that puts us in modern time series analysis, and that's what we would like to be doing in the next 3 weeks. But of course, we'll do a very informed modern time series analysis because you already know classical time series analysis, and that's not the case in a lot of the people that are doing modern time series analysis. Those are mostly people that were trained in machine learning. They may not even be statisticians, but they are trying to get information from time series. So for example, let's put an example. For example, we might want to be we might be interested in classifying epileptic patients based on the episodes that they have. So data, electron, and EEGs, okay, are usually obtained from their brains, and when they have seizures. And there are studies that collect a time series for different types of seizures. And of course, there are different types of seizures. Some of them are stronger, some of them are milder. So instead of using the whole time series, which are really long because they're by second pretty much, they're very long time series. Every second they're measuring the amplitude. So we might just calculate on the average amplitude, the percent of the amplitudes that are beyond one standard deviation of all the ones in each time series. So this is how people do it so that they can use machine learning methods that were not made for time series, okay? So the idea is most of current machine learning for time series is just based on methods that were not designed, like classical time series analysis was designed for time series, but the modern methods were not designed for time series. So people are forcing the analysis so that they can use the modern methods, the methods that are not for time series analysis with time series analysis. So what they do basically is convert the data to a data set that is not a time series data set. So what they do is for each time series, they look, for example, at the amplitude. So let's focus on this example now. The percent of observations that were one standard deviation, the percent of them that are close to the median, whether there is a skewed, the maximum slope observed from one lows to highs, autocorrelation coefficients up to a certain number of lags, partial autocorrelation coefficients, and so on. So then those features might be entered into a decision tree. Decision trees are used very common in supervised machine learning these days, and do random forest and decision trees to determine the type of seizure that that person has, to determine the types or classify. Actually, classification is not supervised learning. Trees are. So for trees, what you're trying to do is predict what kind of seizure a person might have. Okay. Another example that I have done is in unsupervised learning. Unsupervised learning means classification without using other classification. Let's focus on that, right? So here, for example, you have 5 years of the main rivers in California, and here are their names. And they're classified with a spaghetti plot. These are time series of runoff. And there are missing values. This is a longer time series. The whole time series contains the average of April to July runoff between 1930 and 2005 for the major 25 rivers in California. And the plot on the right, just as I said, shows only 5 years to give an idea. There are missing values in the longer series. That causes a problem for our traditional time series analysis, but this is annual data. We cannot aggregate further. I mean, we could do 4 years average to avoid missing values, but then we reduce the data a lot. So in this case, it's not practical to aggregate, so that we can use our traditional classical time series method. So what do? Well, we are going to do something else. What do people now will do? Well, what they will do is, for example, if we didn't know any time series analysis, suppose you don't know time series analysis, you're just a person that is approach with the task of classifying these rivers, and you don't know time series, you don't know anything else. So, and then you know there are missing values, and some time series expert told you, okay, sorry, I cannot help you. It has missing values and I don't want to aggregate annual data. So what you could do is say, oh, okay, I took a stats 10 or some intro stats, and I know about averages, about means and max and number of observations above 2 standard deviations. And you learn these things in your stats class. So say, oh, okay, what I'm going to do is I'm going to summarize the whole time series with a few numbers. So for the river Trinity, I am going to just take the average runoff over the whole period. And remember, this period is from 1930 to 2005. From 1930 to 2005, the standard deviation from 1930 to 2005. So you take each river's time series as if it was one data set. Take the minimum, the maximum, the number of observations that are above 2 standard deviations, and the number of observations below 1 standard deviation. So you consider for that all the rivers, and I don't have all of them summarized here. There are many more. Okay, so there are 25 rivers. But this is what basically people that don't know time series but want to use classification of time series, and or maybe prediction based on time series do. They create features. Features are just the basic summary statistics or some other things that we observe in the time series. And we create a data set that doesn't look anymore like a time series. For each time series, you create a set of features. And that's used a lot in classification. So given those features, then the data set doesn't look anymore like time series data. But if all we wanted to classify the rivers, using cluster analysis, for example, this can be done easily. With cluster analysis, we are measuring the distance between the rivers. The distance is the Euclidean distance between one row and the next row. And so with this cluster analysis, calculate the distances between each of these rows, and you can get 1 point for each river. You might be focusing on 2 features, mean and how many observations are above 2 standard deviations. And then you can, and then what you notice that there is very good classification, right? So if you look at these, the ones, right? There is some rivers that are classified, they separate. You have clusters, and in each cluster you have the same numbers, right? So they have the rivers that are very high, have high runoff, the rivers that have, these are the rivers that have intermediate runoff. These are the ones that have very low runoff. And then we have some rivers that have very high runoff, the number 3, the ones labeled number 3. So these are the ones with high mean, right? So a mean runoff. So these are the biggest rivers. And they're probably in our time plot will be the ones that are here on the top of the picture, right? The picture, the largest, the spaghetti plot, spaghetti that are highest in the time plot, right? So that's one thing. But okay, mean is a deviation. Those are not, those are very basic descriptors for a time series, right? So we know many more things about time series. We have spent 7 weeks studying time series features, even though we didn't call them that way. So we know that the ACF and the PACF tell us about the stochastic process generating the data. We have used them all the time since we learned them. After all, we use the ACF to identify models, right? So there are some authors that wrote a book that is called Time Series Clustering. They show that the autocorrelations are indeed the autocorrelation coefficients, right? As features could be extracted from the calculations we do, and could be used as features, and they are helpful in classifying time series in an unsupervised way. Now, this is great because we know how to calculate autocorrelation coefficients, but we are back to the problem that I mentioned earlier. ACFs work if you don't have missing observations, and they make sense if you have, and they make a lot of sense if you have, you don't have breaks in the time series, the sampling interval is the same for each observation and so on. So even though it's helpful, you may not be able to use them all the time, or you might have to aggregate the data if you have missing observations. So the question is, can the ACF, autocorrelation coefficients, help us discriminate between an ARP and an MAQ process and between white noise? So they showed in a simulation that they can. But of course, remember these conditions. You have to have, for ACF and PACFs, you need to have the conditions of classical time series analysis, complete data, no missing observations, and so on. So let's suppose we have that, and we did that. So we tried to simulate, to replicate what Maharaj and authors found. So I simulated 4 time series from an AR1 with coefficient 0.4, 4 time series from an MA1 with model coefficient negative 0.5, and 4 white noise series. And for each time series, we extracted the first 15 sample autocorrelations, the first 15 sample partial autocorrelations, and then we created another data set, and then we did cluster analysis. And the MAs were all grouped together using k-means cluster analysis. The MAs were all grouped together in one group. The white noise was grouped together in one group. And the ARs were, there was one white noise. I think one white noise was misclassified. Yeah. But, and then the ARs were, one AR is somewhere here. So one of the ARs was put together with the white noise. Because remember, these processes could manifest themselves in different ways. The actual population is an ensemble, remember? So we did cluster analysis, and then we saw that they separate pretty well.